Okay, hello everyone. And my name is Tomi Oravasaari, and I come from the Southeastern Finland University of Applied Sciences. I also have another hat put today here representing the university. And I have the theme about how to detect drones and aircrafts. This is a little bit kind of overview how we see aircrafts in the air. And I try to be not too technical with these issues. Okay, this is the very technical slide at the start, but basically I would like to start that at the moment we have many standard techniques. How do we detect aircrafts in the air? And this is, I think at the moment, this is very interesting in Finland because we have had first of those drones, military drones that crashed in Finland in different sites. And basically, I start from here, and then later in the presentation I go deeper in that. How do we detect those drones that don't transmit their position? The oldest technology is secondary surveillance radar. So basically, this system is it works so that the aircraft has a transponder, and when the radar signal hits the aircrafts, then the aircrafts will transmit back its position. I think this is the oldest way to how the aircrafts will report their position. ADS-B, that's I think very well-known system. It is a global standard, and if you have ever used flight radar or similar systems, this is how they gain the information where the aircrafts are. They just have a wide network of ADS-B receivers which receive these position reports from commercial aircrafts. But because of this, ADS-B is standardized, and it requires a permission, then that's the reason why and it requires a certain amount of power. So maybe this is the reason why the ADS-B at the moment is mostly reserved for commercial aircrafts and maybe for those higher end private aircrafts. Then we have a FLARM, an open glider network. This is a technology developed by a private company. It is very widely used with gliders and light aircrafts, and it has a certain alarming function. So basically with the FLARM, you can see if another aircraft equipped with FLARM equipment is approaching you, and you get an alarm. So it's a kind of detect and avoid system for light aircrafts. Then ADS-L, that's a newer technique. How do we detect drones? Basically, this is designed for the use space and drone integration, and it started in a way that they wanted to develop a system for aircrafts to fit into the use space, airspace. But also at the moment it is it is very useful for drones. And then we have a remote ID, and remote ID at the moment is the way how do we detect commercial drones. So what is remote ID? Well, the initial idea with remote ID was that if you see a drone, then you can take your mobile phone and you can get a ID with your mobile phone from the drone, and this is the way how do you get an ID, and then you can send the ID to officials, and then they can check for you that who owns the drone, who operates that drone. But because the situation have changed, now we would like to see what are the drones operating in the vicinity of area, and we want to detect drones from the long distance. We end up in having a problems here. So basically, because of the low transmission power and high frequency, it means that you need a very special antennas to detect remote ID transmission from great distances. So, but in future, I think more of the drones, at least the bigger drones, will use ADS-L because it has a lower frequency. Lower frequency have a longer wavelength, and it means that longer wavelength can progress better in the air. And this is the reason, and it has also higher transmission power. So in future, I think most of the bigger drones will use ADSL because it's just a better tracking technique. But for at the moment, if you want to see what commercial drones are operating within the vicinity of your area, then you need to be able to receive remote ID from long distances. Then we start talk about how do we detect those drones that don't transmit their position. Quite widely used system at the moment is radio frequency analyzer. So basically this is a device that scans different frequencies and then tries to detect what drones there are in the air. Basically you have two different approaches for radio frequency analyzer. You can use signature library. So basically these manufacturers have recorded how different kind of drones, what kind of radio signature they transmit. And with then when this analyzer detects a radio transmission, it compares it to the library and decides that if this is a drone and what kind of drone this is. And this is the, I think, mostly used method for radio frequency analyzers to detect drones. But now there is also a new kind of approach how to use radio frequency analyzers to detect drones. And this technology is not trying to detect drone signatures, it tries to detect that if this object that is transmitting radio frequency, is it flying object or is it the object on the ground? And basically, when you start to tracking certain radio signals, you can, with a certain antenna constellation, you can track how they progress. And then you can see that, okay, this radio signal is progressing alongside the roads. So maybe it is a mobile phone in a car. And then you can detect that this radio signal is not following roads, and it's moving like a aircraft would move. And this is the way how you can detect that basically this radio transmitter is located on the drone. And the good thing with this approach is that then you don't need to first collect the library, and you don't need to keep updating the signature library, but instead you can just detect airborne transmitters. Then radar. This is maybe one of the more quite reliable way to detect objects in the air. So basically this radar panel transmits signals and listens the echoes from the objects of the object in the air. But the challenge is that the smaller the object, the less it has echoes back. So basically, how to say, the smaller drone, the more difficult it is to detect with the radar. And also, there might be that if the drone is flying in very low level, it might be that then these echoes are mixed with the ground clutter, because you have objects on the ground and those will also give some echoes back. And if the drone is flying very low, it might be very difficult to separate the drone echo from the ground clutter. Also, heavy rain will affect how effective the radar is, because the radar also this, how to say, water in the air, it will also reflect back some echoes. And here in the picture, I have a certain kind of radar. It has a panel, 4 panels, different. Each panel has a certain sector it can survey and detect, and that's why there is four panels to detect 360 degrees. Then acoustic detection. Of course, this is a very interesting one. Basically, you just put a lot of microphones on the area you want to surveil, and then these microphones will how to say, detect all the noise around the surveilled area, and you need the signature library also with this. So basically you are comparing the detected noises to the signal library, and if you detect a propeller noise, then the system will alert that now there is probably a drone approaching the site. And when you have multiple microphones, then you can also locate at where the sound is coming from. You get the location of the drone. The challenge of this system is basically that the drone noises are quite easily mixed with the background noise, and also if you really want to make your drone very low noise, then you can switch the propellers, or if you are flying a fixed wing drone, it will produce quite little noise and it will be difficult to detect. And because of this, the detection range of these acoustic sensors is usually measured within hundreds of meters, whereas the radar, for example, it depends like kilometers, maybe even tens of kilometers with the radar. So, yes, and then what we have next. So basically, then we should also have some evidence that we have actually detected the drone, and that's why usually the drone detection employs cameras. And here I have a picture of pan tilt zoom camera. So basically, if you have a acoustic detection sensor, you then have how to say, the acoustic sensor or the radar will you give an approximate position of the drone, and then it usually then when you connect these sensors, then it's smart to feed the location of the drone for the P-digit camera, and then P-digit camera can take a picture or video of the drone and confirm the detection. And also, the most reliable confirmation of the drone type is usually that if you have a proper picture of the drone, then you can detect what type of drone it is. The visual camera is one. Then you can also use thermal cameras. Then thermal cameras will detect the heat emitted from the drone motors, electric motors, and for example, and then you can also have some low light capabilities with the camera so that it could work during the night time. Also quite, how to say, when you are building the drone detection system, always it's like, how to say, you need to understand what is the threat and what you want to detect, because if you want to detect everything, it will be very expensive. For example, the basic basic RGB camera is quite affordable, but when you have a thermal camera, it gets a lot more expensive quite quickly. Then also GNS interference is important when we are talking about drone detection. So basically, at the start of the presentation, I was talking that there are ways how drones and aircraft transmit their positions voluntarily. We can talk here like cooperative traffic. But all of these cooperative sensors, they detect, they get their position from the aircraft's GNSS receiver. And if there is a GNSS jamming means that the GPS signal is not available at all, or if there is a spoofing, and spoofing means that the GPS position is wrong. So with sophisticated devices, you can give a wrong position for the GPS receivers. And it means that if you have a jamming or spoofing in the area, it means that the cooperative air traffic positions are not reliable anymore. Also, I was talking about this RF detector, which is kind of detecting if the transmitting device is at the airborne device. So basically, this system uses very very precise time calculations when different antennas receive the radio signal, and usually this time synchronization is received via satellites. And if you don't have the satellite signal anymore, then you don't have the time synchronization, and then you cannot do the multilateration, which means that if you receive the same signal with four receivers, then you can get a 3D position of the aircraft. So this is the reason why the GNSS interference is also very important. And last detection method, this is, we go back far away back to history. So it used to be that we had a kind of human aircraft surveillance network around Finland. It was called, in Finnish it was called Ilmavalvontalotta, who were like just watching the sky and surveilling what is happening in the air. So basically, if we want to have a complete system, it means that we also need to employ the visual observations, and when the people see a drone, they need to have some way to report that I saw a drone, it was going in that direction. And when you collect this observation and then how to say, you put this together with the actual observations from the sensors, then you will get how to say, an additional very important level for the drone detection. But none of these systems will work well alone. It needs that you put the sensor data and human observations together, and then you have the, how to say, the best available picture that what is actually happening in the air. Then just one word about the how to say, aviation safety. So basically, when there is a lot of air traffic in the air, it's very important that you are also able to transmit the position of all detected aircrafts to the airborne aircrafts. And this is a picture of ADSB UAT station that we have brought to first in Finland, and I also would say it was first in Europe. We collaborated with certain companies, and we have installed, there is at the moment 3 of these in Finland, one in Pyhtää, one in Mikkeli Airport, and one in Oulu. And all of these stations do that, they transmit the positions of the positions of all the known aircrafts to the air. And this is a countrywide system in USA, but our solution is first in Europe. And there is also some statistics, but they have studied in the USA that this kind of sharing of the location of other aircrafts will significantly reduce the accident rate. So why cooperative surveillance is an architectural prerequisite? So basically, all of these sensors can detect a certain kind of drones and certain kind of phenomenon in the air, but only when you combine the observations, you can make a complete picture. And it's very important that you correlate the observations. So basically, if one sensor sees something, then it's important that you can compare it what another sensor sees. And this is the way how you can make a complete picture of what is actually happening. And if you also add historical data, what has been happening before, you get even better picture. Then you can understand that, okay, this drone we have seen here previously, and we have seen that it is no danger. So basically, that's the way you can. It helps you to detect what are actually the dangerous drones. There is one example from Estonia. On New Year's Eve, there was 62 drones, authorized drones operated over Tallinn to film fireworks. These are drones that we are sending a remote ID signal. And if you have only radar, then you could have seen only like 62 unidentified targets on the air. And if there was one more drone, the 36th drone, hostile drone that enters the airspace, then it would be very difficult to separate like which of these drones is actually a big risk for the city. But if you have the remote ID receiver, then you can straight away tell that, okay, 60 of these are operating legally, or let's say that at least they are following the legal regulations to send their position, and this one is the one who is not sending anything, so maybe it's a bigger risk than the rest of the 62. Okay, so hopefully this presentation gave a little bit overview how we detect drones, and if you have any more questions regarding this, I think it might be better that that after that you can talk to me at the break. Thank you.